Good morning, everybody. Uh, Today, I'll start the topic on desalination, firefighting, numerical problems. So, we'll give some basic about desalination. Already, we have given, but some more details we'll discuss in desalination part, and firefighting already we discussed in another lecture, and we'll try to solve some problem in this lecture. Now, in desalination, we have seen like we have seawater intake. Let's say you take seawater. Okay, so seawater will go to your pre-filtration system. Okay, so like small debris or fishes or anything should not enter. Then after that there will be several sedimentary filter and other filters. Then there will be one pump. So we said that pump will be like very high pressure pump. Normally seawater desalination will be requiring about 60 bar pressure, and then this pump will be delivering the fluid to your RO module, reverse osmosis module. So RO module, when you have, it will be taking seawater, then it will be giving permeate, or this is potable water, maybe water, and there will be another part will be reject. So reject will have a higher salt concentration higher. So many people say this is actually brine because high salt concentration is there. Now, in many cases, especially seawater salt removal process or desalination process, in that case, after RO, there will be sufficient amount of pressure. So that pressure also can be recovered and it can be fed. Okay, so that pump will be working less. So there will be one pressure recovery system. Unit or system, or sometimes a pressure exchanger. So this is actually RO based system. Reverse osmosis based, one membrane is there. So membrane, one side high pressure you create, and salts will not get transmitted through this porous membrane. Rather, only water will be you will getting in another side. Some small amount of salt can be there, but if you increase RO quality or number of RO module, then you will reduce further salt concentration. And salt concentration measured in terms of ppm, parts per million. Okay, so this is called salinity. Salinity of seawater, normally it will be like 35,000 ppm, and it depends on different area location wise also. For example, Dead Sea salinity will be very high, while somewhere seawater is mixing with river water, so say salinity can be lower. So but normally it will be like 35,000 to 42,000 ppm. Okay, within that range. But our potable drinking water will be like about 500 ppm. Okay, and brackish water and other water, those will be ppm maybe 1000, 2000, that range. So because of high ppm or high salt concentration, you need a very large amount of energy to be consumed by the system. Energy, where energy is getting consumed, basically the pump will be taking majority part of your energy. Now pump, if you want to replace, then I already told that wave energy can be one source, maybe alternative source, or maybe tidal energy for your marine systems, or maybe solar, or many other source also you can use. For example, battery operated also possible, battery, but anyway battery will be getting energy from somewhere else to get charged. uh, so pump, if you can use, I mean, if you can use renewable and other sources energy, then your electric consumption or fossil fuel based power requirement will be lower. But if you have normal water, let's say river water or other brackish water, so in that case power consumption is lower. So in that case, like say normal domestic RO plants, they are using very small amount of power. Okay, and now this, when you are having RO plant on your ship or in offshore machinery, so it is only not pump and RO, it is having pre-treatment systems like sand removal process. There will be bacteria cleaning process, ultraviolet UV filter will be there, maybe somewhere there's a permeate you got, then it pass through UV filter, ultraviolet filter. So ultraviolet filter means ultraviolet rays, if it is falling on virus or bacteria, those virus will get disinfected, or the water will be get disinfected, bacteria will be killed. and there will be charcoal filter, so just to remove all the odors. So many other filters will be there. So major part is that pump and RO module. So this is the major part, and major energy will be consumed by the pump. There will be different RO modules, and lots of new research are going on. New materials are coming up. For example, nanoparticle based RO module and other modules are also available these days. So if you are interested, then you can go through this available literature for latest RO module and latest pumping systems. And what are the pumps, what are the different pumps it can be you can use, because this is very high pressure pump and low flow rate normally. So normally positive displacement type you use, positive displacement type. Okay, centrifugal pump, if you want to use, you can remember that characteristic of centrifugal pump like this, HQ, like you can get maximum head, but if you are having, this is centrifugal, this is positive displacement, positive displacement. So positive displacement pump can be like reciprocating pump, your screw pump, your diaphragm pump. Those are positive displacement pump. Even I gave example that human heart also it is a positive displacement pump. So it will be taking certain amount of fluid and it will be delivering. And if you can supply the power, so it can deliver any amount of pressure. Okay, so positive displacement pump reciprocating type can be used. So one type of reciprocating pump is called swash pump. Okay, swash pump or multi-cylinder pump can be used for giving smooth pressure or smooth flow rate to your RO module, because RO module needs smooth pressure, 60 bar about minimum, and if you have more pressure also it will be okay, but normally you have to maintain that bar. If you are not maintaining, then actually your water will not get pushed through the membranes. And for more information, you can go through the YouTube videos for basic simple diagram and simple animation videos will be there. And I have taken content from the book Fundamental of Desalination, and it is given already uploaded in the MIT website. You can download there from there. Okay, now reverse osmosis we already discussed, but let's see some more details. So mammal skin is an efficient membrane, so it controls sweat. For example, our body will be releasing water and body will be cooled, but blood will not go out of the body. Okay, so this is also one membrane system. Similarly, our lungs is there, our kidney is there, so those are also having like membrane system. Okay, so kidney regulates water, salt, iron, proteins, and other nutrients, but it does not allow blood to go out. Right? It will be allowing only water to go out. So at a smaller scale, membrane walls single cell across the mammals, bacteria, and other microorganisms. It maintains cell content like cell. If you have cell, nucleus, and Golgi bodies and other thing, the cell wall also one membrane. So it will allow certain amount of salts and other nutrients to enter into the system. Now industrial scale membrane for different particles. So these are the natural and industrial scale. They have developed different types of membranes. One is microfiltration, ultrafiltration, nanofiltration, reverse osmosis. So you can see this particle size. So microfiltration, it can separate particle 0.15 to micrometer. There is some mistake possibly. So up to 0.15, more than 0.15 micrometer, it can filtrate by more than 0.15 micrometer can be filtered by microfiltration. Ultrafiltration will be like 0.15 to 5 into 10 power minus 2, so much smaller particle size. Nanofiltration further smaller, and reverse osmosis, you can see the smallest particle 5 10 power minus 3 to 10 power minus 4, so 0.000, that range particle can be separated using reverse osmosis membranes. So microfiltration, ultrafiltration, and nanofiltration allows smaller particles to be passing through. But bigger particles are not allowed. Particles are not allowed. Okay, nanofiltration for partial softening of brackish water. So brackish water purpose, nanofiltration you can use. But osmosis and reverse osmosis, it will be like something in solvent, in solid form. It will be separating. Okay, so that's why this reverse osmosis, this membrane is used for your salt separation. See water salt you are taking, you are separating salt, and you are taking pure water or less salt content. Okay, and whenever you are desalinating, normally the people will not go to zero salt thing. Zero salt means you have to give lots of separation unit or lots of osmosis, reverse osmosis, that candles, that will be increasing your cost. Again, you are removing all the salts also required for your body. So certain amount of salt should be there in your water, so that it will be good for health, but not more than certain, crossing certain amount. For example, if more than 1000 ppm salt is there, so that may not be good for your health. But again, if certain chemical is not good for health, that sort of salt also is there in water, that will be problem. For example, arsenic is there in some part in West Bengal, so that maybe that is very much problematic for the human health. So even IIT Madras professor is also has developed some technology to remove arsenic from water. Then they are giving to the people. Okay. So how osmosis and reverse osmosis working? You say first this one osmosis part. Okay. See in osmosis you can see this one salt solvent is there. So lots of salt is there, and pure water is this one, pure water. Okay. So salt will not pass through this one, rather water will be passing through this high density area. Okay, this is normal osmosis case. Okay, and in this case, when low density or low salt concentration water entering, this level of salt concentrated area, it will be increasing. Okay, now this osmotic pressure del pi, the difference del pi is not del p, del pi. So osmotic pressure, you can see this one, this liquid column increased. Okay, and this time del p equals del pi, because your atmospheric pressure or outside pressure and your osmotic pressure become equal. Till is not equal, the fluid will be flowing through this one and it will be maintaining one equilibrium finally. Okay. Now another case, you apply lots of pressure, although salt concentration there, and you are applying pressure, just you are pushing water in opposite way. That's why it is reverse osmosis. So finally what will happen, you are applying pressure or force, because of that you are pushing water towards this one. Okay, so in this case your applied pressure is higher, so applied pressure more than your osmotic pressure, so del p more than del pi. Okay, pi is your osmotic pressure. Now see the some formula. Pi your osmotic pressure and unit is kPa. So pi equals RT summation of xi. So what is R? R is your universal gas constant. T is your temperature in K, and summation of xi is concentration of all constituent in solution, kg mole per meter cube. Okay, and pi value normally it is taken about 0.75.84 kPa for 1000 ppm of total dissolved solids. So total how the solids dissolved, how much is there? So if 1000 ppm is there, so pi value you can take 75.84. Okay, if no value is given, if you can assume, then you use this value. Okay, now SR is a salt rejection. So you have one membrane. Okay, high pressure fluid you are giving, higher salt concentration is here. So high salt concentration and low salt concentration is here. Okay, so SR is salt rejected. So rejected, how much salt will be remaining after removal of water? So the formula is 1 minus xp by xf into 100. Rp means permeate recovery. Permeate recovery means this water, whatever you are getting here, this is called permeate, low salt content. This is permeate, low salt. Okay, So RP formula is there, MP divided by MF. MF, MP means permeate water flow rate, MF feed water flow rate. So meter cube per second. Okay, flow rate. So seawater XF, this is your ppm or salinity. 42, it is assumed 42,000 ppm salinity is there. XP value, XP means your permeate XP, and this one XF. F means feed water, XP means permeate. Okay, so permeate is having 150 ppm and feed water is having salinity 42,000. So your SR means salt rejection is becoming 99.6%. So brackish water, if you take XF is 5,000 and XP 150, so SR becoming 97%. Okay, so currently the membranes can separate salt about 99%. So it's very high performance membranes are there. Now how this whole system in RO based system is there. RO based system is having one chlorine dosing pump. Here you have to add chlorine and you have to remove certain amount of salt using chlorine. Feed is coming from here, seawater. Okay, then it will be going through one mixture because you are adding chlorine and you are adding seawater and mixing. After mixing, you are passing through carbon filter. So carbon filter also will be removing certain amount of solids. Then again it is going to static mixture because you are adding certain amount of acid. So basicity you are removing and you are adding small amount of pH. Now it will be going through cartridge filter, then membrane. So before membrane there will be one high pressure pump, then membrane module will be removing brine and it will give your permeate. Permeate means potable water, and brine means you have a higher amount of salt. Basically sodium and chlorine ions will be more. So whenever you are separating salt, majority portion will be sodium and chlorine or sodium chloride. Now some formula. So permeator mass and salt balance, MF equals MB plus MB, XF MF and equals XP MB XB MB. So you can see this MP is water flow rate through the membrane, P bar and pi bar is feed side average hydraulic osmotic pressure. So you can draw this one. This is a high salt concentration area, this is low salt concentration area. Okay, so water flow rate through the membrane MP. So that means is permeate, P means permeate. Okay, pi means the osmotic pressure, P is your average hydraulic pressure. Kw water permeability constant meter cube per meter square second, kPa. So when you have membrane, so it will have some constant, water permeability constant. A is a membrane area. So how much area is there in a membrane? So that is A. Now water transport semi-permeable membrane through. So MP formula is there. MP equals del P minus del pi KWA. So just you should remember this formula. So del P equals P bar minus PP, del pi equals pi bar minus pi B, and P bar and pi bar also calculated using formula like 0.5 PF plus PB, and in both cases pi F plus pi B. Now for salt transportation, you have one formula, MS equals X bar minus XP KSA. X bar formula is this one. Okay. So permeate salinity XP equals MS into MD. MD means actually discharge or permeate amount. Now we have seen the formula for RO based system. Now we will see MSF or multi-stage filtration system. So here you have intake seawater, you are taking from here, intake seawater. So it is intake seawater is lower temperature. So this lower temperature it is going through like this. Okay, then again coming like this, coming like this. Now another water you are taking, the intake water, same water you are heating here, it is coming through this one, and you are giving heat. Okay, you are giving heat means you are increasing probability of creating steam. Then that hot hot water will be passing through this boxes. Okay, 1 2 3 4, many boxes are there, it will be passing. Okay, what is passing, what will happen, actually it is low pressure zone. When low pressure is there, this hot water will be releasing lots of steam. So lots of steam will be that steam will be going through this one, and here we have cold coil. Okay, so cold coil will be condensing certain amount of water, so that water will be collected here. You see this one collection part, and you are getting distilled or distillate product. Okay, now whenever this steam is moving from low pressure liquid layer to steam zone, so there is one demister. Okay, demister is like one mesh will be there, like mesh is like this. Okay, when what vapor is going, and if any liquid particle is there, it will be caught, and the liquid particle will be forming liquid droplet and it will be falling down, and other steam part, pure steam, will be moving up, it will be getting cooled down here, it will be falling, and you are collecting distillate product. Now first stage will be giving certain amount of water, again you push towards second stage, the water will be moving to second stage. This 1 2 3 4, so many stages are there. So second stage, again it will be getting certain amount of water. Third stage, again it will be entering, again you are getting certain water, so you may have 30-40 stages. Again finally you are getting distillate product, but in this case you are using limited amount of power, because any waste heat also can be given to increase your brine or this heater or heat here in heat exchanger. This is heat exchanger. Okay, and finally whenever you are getting water, so that water, you can see this last stage, it will have higher brine, higher salt. Okay, so that salt again you can put into your system, again recycle the whole water. Again some salt, if salt content very high, you can reject this one, and you can take fresh water from sea and again recycle the whole system. So MS flashing stage, you can see the single stage of flashing, how it is working. Okay, let's say inlet brine you are taking here. Okay, then you are putting this one inside this, and pressure is lower here, pressure is low. When pressure is low, lots of steam will be coming up, lots of vapor will be coming up, and will be passing through this one. Okay, and it will be going through demister. This is demister. Then this steam will be passing through this cold tube bundle, and when cold tube bundles are there, steam will be condensed and will be creating one layer here. So that steam you take, distillate. Okay, this is one single stage, and if you have multiple stage, then again you can create another stage. You take distillate, and whatever remaining brine is there, so that brine you send to another stage, so that way you collect lots of amount of water. Now we have seen that RO module, this flash distillator system, you have flash distillator 1 2 3 system, like brine, high temperature brine entering, then demister is there. Okay, then you have cold coils. Okay, now pressure low, this pressure further lower. So when pressure is low, how to create the low pressure? So previous lecture we have seen that we have one ejector system. So ejector system will take water, it will create low pressure, then water will go back, but that low pressure will be used to handle your high volume of steam. So how this ejector is working? So ejector principle is just, it will be working basically based on Venturi principle. Okay, So venturimeter, you may have seen your undergrad class laboratory. Venturimeter will have like two pipe and one manometer will be there. This is manometer. This is called venturimeter. Venturimeter. Okay, this is flow rate Q1. This is location 1, maybe this is location 2, this neck location. And I have here one mercury column. Okay, so maybe Hg or anything, any suitable fluid here. Now because fluid is passing through this one at very high velocity, because narrow area is created, so velocity will be increasing. So velocity when increasing, pressure will be dropping. So that is called Bernoulli's principle. P1 by rho g plus V1 square by 2g plus rho plus z equals constant. Okay, z means height. Okay, P is pressure, rho density of the fluid, I'll remove one. I'll make general equation first. Density of the fluid, and V is the velocity, and G already you know, 9.81 meter per second square. Z is height, or yeah, height of the pipe. Now I have 2.1 and 2, one pipe diameter larger, two pipe diameter smaller, a narrow section, so it is creating venturi. So at 2, because of high velocity creation, your pressure will be lower. So when pressure is lower, if mercury column is there, it will create this difference H. Now how much pressure is pressure loss is there, or pressure difference is there? So H rho G, this will be pressure difference. Okay, or del P. Del P is created like H rho G, and if we know rho means rho, maybe H rho dash equals fluid in the, okay, this main pipe fluid will be different and manometer fluid will be different. So manometer fluid is say mercury, then it will be 13.6 gram per centimeter cube. Now this laboratory setup will be there all over in majority of the engineering colleges, because this is basic test how this venturi creates low pressure. And this is this calculation, this pressure, how much pressure drop will be there, the calculation can be obtained from your Bernoulli's principle. Bernoulli's principle, nothing but this is an energy equation. Okay, and we are assuming that there is no energy loss because of friction and heat transfer and other losses. So we are assuming no energy consumed. Okay, and there is no other loss, then you can calculate directly from this formula, P by rho g plus V square by 2g plus z equals constant. Now ejector is created based on your venturimeter principle. Okay, ejector will have like this, one design, then it will have design like this. So 0.1, this is 0.2, this is 0.3, this is say, this is 0.4, this is 4, maybe this is 5. Okay, let's say fluid is moving from 0.1 to 0.2, again 0.2 to 3, 3 to 4, 4 to 5, 2 to 3, 3 to 4, okay, 3 is below, okay. 2 to 3, 3 to 4, 2 to 4, 4 to 5. Now how we are creating vacuum? Say high velocity fluid is having P1 Q1 flow rate, and density, let's say constant density rho, and velocity V1, Then what is the velocity of 2? So 2 at point 2, P1 by rho 1g plus V1 square by 2g plus Z equals P2 by rho 2g plus V2 square by 2g plus Z2, whatever it say, because let's assume the pipe is horizontal, so Z1 equals Z2 for equals 0 for horizontal pipe. Now P1, pressure at 1 and pressure at 2, we can calculate. And what is the velocity? So velocity V equals Q by A, flow rate divided by area. So V1 equals Q1 by area 1 and V2 equals Q2 by area 2. Now area 2 means the diameter changed, so area changed. Okay, now I can calculate velocity from this equation. Maybe I can put number 1. From equation 1 I can calculate, if I give you pressure you can calculate velocity, or if flow rate is if some parameter is missing you can calculate other parameters. Okay, and now this main fluid is called primary fluid or suction fluid, primary fluid or motive fluid or power fluid. Okay, main pipe is having primary fluid, motive fluid, a power fluid, and this one 3, at 3 it will be like, this is called suction fluid or secondary. Okay, now after venturi, this area is called mixing chamber. Mixing chamber, CHAMBR, and this area called diffuser. This is called nozzle. This is called nozzle. Okay, nozzle will have lesser diameter than main pipe. Now mixing chamber is the purpose. Mixing chamber actually it will be mixing primary fluid and secondary fluid. So fluid coming from 1, fluid coming from 2, it will be mixed up properly in mixing chamber. If mixing is not proper, your performance will be decreasing. So proper mixing is important in mixing chamber. So to give proper mixing. And what is the purpose of diffuser? I have written, like you can see this diffuser, I have written that wider section. So wider section actually it will be reducing fluid velocity and it will be increasing static head. Okay, kinetic head will be converted into static head at diffuser. So the purpose of diffuser, kinetic energy will be reduced and pressure energy kinetic energy will be reduced and static energy will be increased. Mixing chamber is mixing only, it is not changing velocity and pressure, but diffuser is changing that one. Okay, nozzle's main work is to change pressure to velocity or velocity to pressure. Now you should remember the terms, because whenever you are talking about creating low pressure, so the suction fluid, this is creating vacuum. This is creating vacuum or low pressure in your MSF system. Okay, in MSF system you are creating low pressure, and because of low pressure you are creating lots of steam or vapor. So that is giving that low pressure is giving you the distilled water.